Hello, I'm Paul Beckwith. The purpose of this video is twofold. The first thing is to discuss the global oceans, the latest science on all different aspects of the oceans, including temperatures, ocean currents, salinity, density, and the state of the El Nino Southern Oscillation, and all kinds of different aspects of the ocean as they appear in the BAM's State of the Climate in 2020 report. The second purpose of this is to introduce you to this little mop, little girl mop, and she's a bit camera shy. She's a version of Shackleton, a little bit heavier, but with a little bit more fur. And she's only getting comfortable on the camera. She doesn't like being held. When she was a little kitten, you'd pick her up and it would be instant purring. But she's become a bit of a recluse with the coronavirus, so we have to try to wean her off that. Okay, so let's get right into the state of the climate in 2020 global oceans. And again, download this report. If you just Google Bulletin of the American Meteorological Society, State of the Climate in 2020, full access. You can go to the PDF. You can get a high-resolution version of the PDF, which is better, and then the figures all appear much clearer. Okay, so I'm going to talk about the state of the climate, the global oceans. I'm going to do it with, by going through the figures and explaining the figures in the report. Okay, so here we have two maps. And we have the sea surface temperature anomaly in degrees Celsius in 2020 in this map. And this is relative to the climatological, the 1981 to 2010 average. And in B, we have the difference in sea surface temperature between 2020 and the previous year, 2019. So what you can see is that we're getting specific areas of a lot of warming. Up here in the Pacific and the North Pacific, both the Western Pacific Ocean, the Eastern Pacific Ocean, the eastern part, significant warming. This is 1.5 degrees Celsius anomaly. Here, this is what people have called the Blob, okay, in this particular region here. There's also significant warming off the eastern seaboard of the US here and up into the Labrador Sea. And there's also, of course, significant warming up in the Arctic. But what you can see here, so what's happening here is, and you get a cold area here, or a global warming hole if you like. So what's happening is the Gulf Stream comes up the coastline here, and it's slowing down and it's getting stuck over the coastline and in this region. So the heat from the Gulf Stream is being released here, and less of it is going across to Europe. Okay, so the Gulf Stream is definitely slowing down. The AMOC, the Atlantic Meridional Overturning Circulation, is slowing down. So there's more heat stuck in this region. That heat's not being transported up over into this region. So it's getting stuck down in this region. It's also getting more stuck in this region here. You have the whole circulation pattern. Okay, and I would argue, and this is not talked about really too much at all, but I would argue, over here in the Pacific, we have the same sort of gyre. We have the Kuroshio current coming up here, and we get this gyre coming like this. Okay, and this heat is not, this heat is, I think the gyre is behaving differently in the Pacific as well. The heat is coming up here, and it's not being released out of the system like it was before. Here, the Gulf Stream would come across, it would lose heat and cool down with the Arctic, and then the water, the dense water, would descend deep to the bottom of the ocean floor, completing the conveyor belt system. And here the same sort of thing was happening, but because the Arctic is so much warmer than it used to be, we're not getting this water cooling enough to descend down to the deep ocean abyss, so it's staying on the surface, and that's why we're getting these huge anomalous hot temperatures in the Pacific and also in the Atlantic. Although the heat is not getting up to this region, it's staying lower in the Atlantic, but it's still going across and getting up into this region, but then it has nowhere to go, so it's just accumulating in this region. So I think these temperatures that we see are artifacts of the greatly warming Arctic and the decline of Arctic sea ice, because when the ice is formed, the fresh water is mostly taken up into the ice, so the salt is rejected, making the water denser, and then it would sink down to the bottom of the ocean floor, and that's not happening, so the water is being stuck on the surface. This is the difference between 2020 and 2019. You can see that this region here, 2019 had a very similar pattern because there's not a lot of difference here, but these regions here were actually warmer in 2020 than they were in 2019. So it paints a consistent picture. This is the sea surface temperature anomalies, and this is throughout 2020, but this is for the different 3-month period. So this is December, January, February 2020, the anomaly relative to, again, the 1981 to 2010 climatology, or that's the baseline if you like. So this is January, February, March, April, May, June, July, August, September, October, November, December. And you can see the huge, you can see how the seawater warms up throughout the year, how the warm pockets shift or intensify. You can already see the blob here getting stronger and stronger through the summer months, and the anomaly is the largest actually in the fall when things should be cooling off, because it's not cooling anywhere near as quickly as it used to. And again, you see the same sort of hot water off of the eastern US, you can see the progression here of the, there's no ENSO, really it's neutral here, but then it starts to build up into a La Nina, where this area is cooler, and the La Nina gets stronger as you reached into the end of 2020. Okay, so that's the sort of pattern that you can see, and again, the Arctic is warming so much that we're not able to, the water going up north is not cooled enough, so it just circulates around in the basin. Okay, so the huge Arctic warming is affecting everything on the planet, including the ocean currents. Okay, and we just covered this, so let's go down. Okay, so this is the trends in sea surface temperature anomalies in degrees Celsius per decade through different databases. So if you look at it globally, it's about the average of these four numbers. It's about 0.14 to 0.20. So call it about 0.18 or something. 0.18 degrees Celsius increase per decade in the sea surface temperature anomaly. So that's the rise per decade. So it's very, very large. And you can look at specific regions, and you can see that the North Pacific is warming faster than anywhere else. It's 0.36 degrees Celsius increase per decade. Okay, and the tropical Indian Ocean is the next in terms of the increase of warming, and the part that's warming the least is the Southern Ocean. Again, you can see that reflected on all of these plots. The Northern Pacific warming like crazy, the Indian Ocean also warming significantly, Southern Ocean it's got the largest volume, of course, the huge mass of water is warming the least. So that's all consistent. This is the plots over time from 1950, in this case, to 2020 of the global ocean from the four different groups doing it. And you can see the rise of the, and this is relative to the 1981 to 2010 baseline again, I believe. Okay, 1950 to 2010. 2020. It doesn't. The baseline is somewhere here, about over. It's a bracket around 2000 because that's where it crosses through zero. So anyway, global ocean rise. This is global ocean from 1880 to 2020. This one's more recent, 1950 to 2020, which would fit on the graph from here to here, basically. So if we expand it to 1880, you can see the rise in the global ocean temperature. The oceans are taking up more heat than anywhere else on the planet. 91% of the heat warming the planet is going into the oceans. This is the tropical Pacific, so there's a rise here. This is the North Pacific. So from about 2000 onwards, there's been a massive increase in temperature in the North Pacific, almost a degree Celsius. Okay, this is huge. In the tropical Indian Ocean, there's been a steady rise. In the North Atlantic, there seemed to be a break near around 2000 where the temperature went up significantly. Tropical Atlantic, steady rise, and the Southern Ocean, a steady rise, but the magnitude is a bit lower. I mean, this is only going up to 0.2 or so from roughly minus 0.4. So that's a 0.6 rise in the Southern Oceans in the last 70 years, whereas if you take the the North Pacific, it's going up. It's been going up about almost a degree since 2000. Huge and frightening rise of water temperature. Okay, so this is the Northeast Pacific Marine Heat Wave, or the Blob, in 2019-2020. There's two images here, and I think the text is wrong. I think this is June, July, August in 2020, and September, October, November in 2020. I think this should be 2020 here. So you can see, the blob here, this very, very hot water in the North Pacific, both in the summer and in the fall of 2020. This is the temperature anomaly with respect for the different depths. So the surface, 200 meters down below, and you can see the marine heat wave in about 2015, the first blob in this region, and this is the blob in the 1919-20 case, and it looks like from this, it looks like the 2015 case was a bit stronger. This is the salinity with depth, so it's the grams of salt per kilograms of water. The salinity, okay, and you can see that so this is fresher, is the greenish, bluish, and the brown is saltier. So it's saltier. Okay, so it's hard to correlate these to the temperature. There's other things going on with current, etc. And this is the density of the water in kilograms per cubic meter, the anomaly. Okay, so the water's a lot hotter here, so it's a lot lighter. It's got a negative density anomaly, and the water is cooler in these regions here. So the water is heavier. The anomaly is heavier. Okay, so moving on. This is the ocean heat content. Okay, this is the in situ ocean temperature data estimate of the upper 0 to 700 meter ocean heat content. Okay, so we see this is in terms of joules per square meter of energy. The redder the areas, the hotter the water, the more heat that the ocean has retained, and you can see the heat here and here. Again in these regions in the North Pacific, and again here in the Atlantic off the U.S. coast. Okay, so this is a 2020 anomaly relative to the 1993 to 2020 baseline. Okay, and this is 2020 minus 2019. This is the change in 2020. So you can see, that the hot regions got exceptionally hot but there is some blue interspersed, so there is fluctuation here. And then this is the 1993 to 2020 trend. Tremendous warming, tremendous heat stored in the ocean, both in two areas here. And this is related, I'm pretty sure, to the ocean circulation patterns, because we get the Gulf Stream coming up here and it's slowing down and spending more time over here, so there's a huge amount of energy that is going into the ocean, that is stored in the ocean in this region, less than normal in this region, the global warming hole. And the same sort of thing, if the AMOC is slowing down, then I'm sure that the Pacific version with the Kuroshio current and stuff is also slowing down, because we see these different artifacts here. But you'll find very little in the literature on the Kuroshio current and what's happening to the ocean circulation in the Pacific. Okay, so let's continue on. So this is the ocean temperature anomalies from 2004 to 2020, and the pressure. So going down deep through into the water column with depth. So this is the surface of the ocean. Okay, so obviously getting a lot of warming, and this is from 65 south to 80 degrees north. So it's an average. It's the average monthly ocean temperature anomalies. Okay, and what you can see is that so we've had tremendous warming, from 2016 onwards, pretty much, at the surface of the ocean, and that's extending deep down to the ocean floor. Okay, this is the anomalies here. This is all warming, and the trend in degrees Celsius per decade is it's relatively slow as you're deep. But when you come to the surface, we're talking about 0.2 degrees Celsius per decade warming at the surface. Okay, phenomenal warming. This is showing, these are showing some of the trends, the 0 to 700 meter depth, the warming over time. And this is deeper. This is the deep ocean heat content up through so 700 meter to 2,000 meter. Basically, different curves, okay, and you can see, there's an awful lot of heat. This is the heat going into the upper layer, 0 to 700 meter layer of water, and this is the heat going into the bottom layer. Okay, so the heat in the upper layer is, of course, much greater, goes up to 180 zetajoules. This only goes up to about 80 or 90 zetajoules, about half. But the whole ocean column is heating. Okay, this is the global ocean heat content trends in terms of watt per square meter for the three depth ranges. 0 to 700 meter from different groups, so it's about 0.37 to 0.41. It's about 0.39 watts per square meter heating in the 0 to 700 meter level of water, and it's about, there's more variation here, say 0.15 to 0.31. It's say 0.2 say watts per square meter average. Okay, so slightly more than half is going in the 700 to 2,000 meter column, and about a third of what's going into the mid column is going into the deeper column, 2,000 meters and below. Okay, so the whole ocean column is warming. Now this looks like sea surface salinity. So this is the sea surface salinity in parts per, these are in PSU, practical salinity units. Okay, so this is parts per thousand, which would be, so 34.5 parts per thousand would be 33.45 parts per hundred, or 3.45%. Okay, so this would be 3.45% salt, and these are the isocontours. So we have noticed a couple things. The Atlantic is always much saltier than the Pacific. One of the reasons is that when you get evaporation of the water from the Atlantic, The continents are closer, so that rain can be carried across to a continent and deposited, leaving the ocean saltier, whereas the Pacific is much wider. So when you get the evaporation, it will likely fall in the Pacific again, rather than go onto a continent. So it's not as salty in the Pacific, it's saltier in the Atlantic, and you can see where the salinity has increased. So there's probably more evaporation in those regions. The water is warmer, so there's more evaporation, so the salinity has increased. And you can see there are regions where it's decreased as well. This is the difference in 2020 minus 2019. So there's some regions where it's significantly larger here. This is related to the state of the ENSO. And then if you look at the overall trend from 2005 to 2020, you can see these areas here are becoming saltier. There's areas here that are becoming fresher. Okay. This is sea surface salinity anomalies for December, January, February, March, April, May, June, July, August, September, October, November. So you can see the seasonal effects of the salinity over time, and it should be important to point out that in general the salinity of the ocean has not changed for a large period of time, but there's lots of regional variations depending on amounts of rainfall, things like that, temperature of the water, how much water is being taken below the surface, etc. So the vertical mixing and so on. These are monthly salinity anomalies from 0 to 1,000 meter deep for the Atlantic, the Pacific, and the Indian Ocean basins through the years from 2011 to now. And you can see again the brown areas are increases in salinity. It's getting saltier, and the blue areas the water is getting fresher over time. And then these are plots of the salinity change with depth, how it's changed from how it's changed over the time period. And this is showing the anomalies. This is the zonal 0 to 500 meter zonal average salinity from 2019 to 2020. Okay, how it's changed with depth and as a function spatially. So from 60 south to 60 north. So imagine taking a slice and looking at the depth, and you can see that there's different bands that you can see. So different regions, different latitudes have different salinity anomalies, slightly higher or slightly lower. This is the salinity trends from 2005 to 2020. Okay, at standard for the Atlantic, Pacific, and Indian Ocean basins. So the red line is the zero trend line, and you can see an increase in salinity in the Atlantic Ocean, increasing to the surface where it's maximum at the surface. And you can see in the Pacific, it's actually lower at the surface, it's fresher, and then it gets higher as you go down into the water column to 120, 130 odd meters, and then it goes back to the trend line. And in the Indian Ocean, not much change at the surface, and it goes a bit saltier with depth, similar to the Pacific. Okay, this is surface heat flux. Okay, so this is where the heat is, positive values denote ocean heat gain. So negative values would be heat coming out of the ocean. Okay, so the blue areas are, the heat has come out of the oceans. The red areas are the oceans have gained heat. And this is, okay, so this is, the first one is 2020 relative to the 2001 to 2015 climatology. So you've seen the areas, the red areas that are gaining heat, and the blue areas where there's a negative anomaly. Okay, then B is 2020 minus 2019, the differences. So just the areas in 2019 that heated and cooled, or 2020 that heated and cooled relative to 2019. This is the surface radiation, short wave and long wave, and then turbulent heat fluxes. Okay, and then there's other stuff here on these. This is surface freshwater anomalies. So this is basically, if you take precipitation at any location, subtract the evaporation at any location. If precipitation is much larger, then that area should get fresher. And if precipitation is much less than evaporation, then that area should get saltier. And this is how this is shown. So B is this is precipitation minus evaporation. This is just the evaporation, and this is just the precipitation. So less precipitation here, more precipitation in these areas. So when you take the difference, so the key is the flux here, and this is relative. So this is relative to the 1988 to 2015 climatology, and this is just relative 2020 relative to 2019. Okay, so you can see the long-term trends in surface fresh water. This is the wind stress. You can see where the wind is stronger and weaker on the surface of the Earth. You know, lots of stuff going on here depending on whether El Niños and La Niñas are happening. Okay, so this is global mean sea level. So right here, the black line. And if you take the steric level and the ocean mass level, so that you're adding more water from melting glaciers, etc., and you're taking the expansion of the ocean, right? Warmer water expands, and you add these together, you can get this curve here, ocean mass plus steric sea level, and it matches with the observations here. This is very interesting here. This is where this is the change in sea level rise from 1993 to 2020. The regions with most sea level rise, up to 200 millimeter over this time frame, are the dark red areas. Okay, and you can see sea level rise is very large off the eastern coast of the U.S. One of the reasons is that the Gulf Stream has slowed down. The water's piling up here. The water is very, very warm in the North Pacific, and sea level rise is therefore larger because the water is expanding and bulging. And you can see the other regions here. So you can see how there's a big variation over the planet with sea level, but most places it is rising. You know, here is a region where it's not rising as much, for example. Okay, so there's a lot of information given there. This is the sea level anomaly in 2020 relative to the average sea level at each location during 93 to 20. So I'm showing, so that's basically this plot again here. Okay, and this is 2020 minus 2019. So you can see there's been lots of sea level rise here because the water is a lot warmer here in 2020 versus 2019. This is the average sea level anomaly during December, January, February 2020 relative to the 1993 to 2020 baseline. Lots of rise here and here. And this is in September, October, November, and you can see the rise is much less here because the water is cooler here because we've gone into a La Nina condition. These are areas where there's coastal flooding. They call it nuisance level flooding thresholds. Different regions, it looks at the number of days on different coastlines around the planet where you get nuisance flooding. You don't get, there's no storm surge, there's it's just sunny day flooding happening more and more often because of sea level rise. This is zonal current anomalies, okay, and current anomalies, and I'll just go on here. Zonal velocities. Okay, so there's all kinds of different parameters looked at. This is a meridional overturning circulation. Okay, there's different markers here, buoys, to measure the water flow at 26.5 degrees north and up in some of these other regions and in the southern hemisphere. And the meridional overturning circulation in sphere drops is decreasing with time. The trend is down. So the Gulf Stream coming up, coming across, recycling, this whole pattern is weakening over time. There's lots of other data teasing that out, but that's the key result. And yeah, basically Okay, this is interesting. This is showing the distribution of plankton. So if we look at chlorophyll A, that's the active chemical in plants where photosynthesis is undergone. We monitor that from satellites. This is the carbon from photosynthesis and sea surface temperature anomalies. This is the 15 degrees Celsius line. Okay, and what you can see is so this is the chlorophyll A. Lots of chlorophyll A in these regions. Okay, in the southern hemisphere, not so much in the northern hemisphere. That's a clear factor. Okay, and also the carbon stored from photosynthesis is you can see it more balanced across the planet. And the sea surface temperature anomaly, I was talking about this before. Okay, so you can try to relate that to the phytoplankton, and you can see the where the phytoplankton peaks in the summer month. This is chlorophyll A where it peaks. This is across the year of 2020, and you can see where it peaks in the northern hemisphere and where it peaks in the southern hemisphere. Okay, they're pretty much out of phase. And again, there's some plots of the chlorophyll A and the anomalies and so on. 23-year record. Okay, so all of this is being studied. Ocean acidification status. Okay, so this is around the Pacific Ocean, and you can see this is the fraction of CO2 that's absorbed in the water. You can see regions where it's high and where it's lower, and this is the pH of the ocean. So a ship made this traverse, and it measured the pH, and you can see 8.05 is the greenish. It's extremely high up in the red regions here and near some of the coastlines, and it's lower over here in the open ocean. Okay, so the global annual and monthly net CO2 fluxes in petagram of carbon per year in the oceans. And you can see that it's decreasing. Okay, the sink of the oceans as being a sink for carbon is decreasing. This is the net air sea CO2 fluxes. Ocean CO2 uptake regions are in blue. Okay, so the blue regions are where the ocean's absorbing huge amounts of CO2. The red region is where CO2 is being released to the atmosphere. No surprise here, because the water is very, very warm at the equator, and warm water cannot hold much dissolved gas, CO2, oxygen, anything. Okay, so any CO2 that comes into this region, if the water is heated, if it's in the water column that comes into this region, then it ends up in the atmosphere. These are the areas that are the huge sinks of CO2 for the planet. Okay, and then there's temp. This is like the SST, sea surface temperature, the fraction of CO2 absorbed in the ocean water, and the El Nino index, and it shows how it varies and how it fluctuates from year to year, and you can see what happens in the El Nino years here and here. Okay, this is a dissolved inorganic carbon in the atmosphere at different depths. And I think I'll finish off here. Okay, so I highly recommend you download this report and look at this entire section on global oceans. Thank you for listening.